All right, today we're going to dive right into the study of median finding, which I outlined for you last time. I obviously don't need to define the problem. I will remind you that although I'm talking about median finding, everything that I'm saying generalizes to the general problem of finding the kth indexed item in a list. As I mentioned last time, you've already analyzed quick-select, the algorithm that is an analog of quicksort. It takes some constant number of comparisons per item in the list in order to find the median in expectation, but the constant is somewhat larger than 2. There is a deterministic lower bound. Title, median. There is a deterministic lower bound. Which says you need at least 2 plus epsilon times n comparisons in order to find the median. And I'm going to talk to you about how random sampling can beat that. And I want to break it out in 2 separate useful concepts from random sampling. The first is about how random sampling can be used to very quickly approximate the solution to a problem. And the second is about how you can often use that approximation as the starting point for quickly finding an exact solution to the problem. Okay. So we are going to explore random sampling. And the intuition, which essentially drives all random sampling, is that a small sample is somehow representative the whole. Okay? So let's start with the easier goal of imagining some kind of approximation to the median. Okay. What would it even mean to define an approximation to the median? Should we look at sort of a numeric approximation that, we're within 5% of the value of the median? Yeah.
Maybe that, like the median that, or the thing that we discovered there is like that kth index, like of the list, where like k is something between like 0.45.
Good. So you're suggesting that we should look at the index of the item that we return. Why is that more appropriate than looking at the value of the item that we return? Yeah. Exactly. We're looking at comparison-based algorithms, and the values of the numbers don't matter. It's just the orders. And so, you can take any problem with a particular ordering, and if you have some, guarantee on the value of the approximation, the numeric value, you can imagine doing crazy things like just exponentiating every number, which would give you a much better approximation, which would let you solve the problem exactly through approximation. Those of you who took advanced algorithms with me last year know about these amplification techniques that can improve the quality of an approximation if it is not measured properly. And so working off the numbers would be a very fragile notion of approximation, but working off of the index does. So what we might hope to get here is an index that is close to n over 2, right? And the question is how quickly we can do this. And I'm not going to do this in great detail. I'm going to be very sloppy just to get the idea across. So imagine that we choose some number s of samples from the list, and I'm going to make what initially might seem like a weird decision. I'm going to be choosing these samples with replacement. What that means is that when I sample an item from the list, I don't take it out of the list, and it may get sampled a second time. Okay? And as we will see over the course of the semester, sampling with replacement may be counterintuitive, but it tends to lead to much less messy analysis. Okay, because if you're sampling with replacement, every sample is independent of every other sample. Right? If you take items out, then you have to say that, well, I know that this sample is different from that sample, and those things are no longer independent samples from the entire set. So the analyses all still work, but they just involve a lot more math for no real benefit. So I'm going to choose S samples with replacement. And what would be a natural thing to take as my approximation to the median of the entire set? Yes? Sure. What can I say about the median of the sample? Okay. Can I somehow argue that it is close to the median? Right? Let me add some notation here. So I have my initial set, which I'm going to number as x1 through xn. And I'm going to assume these are in order. So the indices are the indices of the items in order. And I'll call my sample x1 prime through xs prime. They're taken out of the entire set. And so we are going to be looking at x sub s prime over 2 as our candidate median. Okay. So we want to argue that this is close. So let me have to come up with a sort of a definition of being far. I would say that this is a very bad approximation if, for example, this sample is among the first quarter of the items in the original list, right? That would make it a very bad sample, a very bad approximation, right? So maybe we can talk about the probability that this happens. And correspondingly, on the other side, we can ask about the probability that this sample is above the 3/4 point. These are symmetric, so it's going to be the same analysis either way. And if I prove that neither of those things happen, if I say that my sample median is within the middle half of the entire list, I've just made a kind of approximation claim, right? It's not a great approximation claim, but it is a meaningful approximation claim. So how can this happen? Yes. More than S over 2 of the... Okay, more than S over 2 of the sample are less than N over 4. Yes? How do we analyze that probability? Yes. Good. Independent samples. Each is less than x sub n over 4. Let me fix this. With what probability? Yeah, 1/4, right? Okay. So what does that tell me about the probability that at least, or what kind of probability distribution am I looking at for the entire sample? Yes?
Well, the number of samples that are less than X out of the binomial.
Exactly. So the number that are less than x sub n over 4 is a binomial distribution where I have s samples, and each of them is a bad sample with or a small sample with probability p. Yes? So we can immediately read off our probabilities. Whoopsie. Probability that I get k of these is equal to s choose k, p to the k, 1 minus p to the n minus k. Yes? And I can do a whole bunch of math to figure out the exact probability that we get too many. But as a lazy computer scientist, I don't like to do math. I like to use tail bounds, where I can get rough approximation to things in a very straightforward fashion. Right? So I will now remind you of the Chebyshev bound, right, which we talked about last time. What I claimed for the Chebyshev bound was that the probability that any random variable, and this applies to, it doesn't matter if this is a non-negative random variable or not, the probability that a random variable deviates by more than t times its standard deviation from the mean is less than or equal to 1 over the square of the number of standard deviations, right? Or equivalently, the probability that the deviation exceeds some bound is less than the square of the variance divided by the square of the deviation. Okay, that's just changing the units to absolute instead of units of standard deviation. Okay. Yes?
Why don't you use the Chernoff bound?
Because I haven't taught it to you yet. I will teach that at the end of this class, and we will use it for other things. There's a reason, but there's actually a better reason for me to use the Chebyshev bound, which I will reveal to you in about 45 minutes. Okay? It lets us do things that we can't do with the Chernoff bound, strangely enough. Okay? All right, so nice thing about the one more valuable thing about the Chebyshev bound, why it is so applicable to the kinds of algorithms that we develop, is that the standard deviation for a sum of random variables, okay, is equal to the sum of the the variance of a sum of random variables is equal to the sum of the variances if the random variables are independent. And we carefully design our algorithms to be full of independent random variables so that we can sum the variances. And that is, in fact, one of the reasons I chose to sample with replacement, is that I get independent random variables for this binomial distribution, which means I can sum the variances. In particular, if I am looking at a binomial with these parameters s and p, it's just a sum of indicator variables, right? Where each I is equal to 1 with probability p, right? Just counting the number of times I get a success or a particular outcome. And so I can talk about the sigma of one of these indicator variables. It's equal to, with probability, sigma squared. With probability p, the value is, running a little too fast here. Right, so this is equal to the expectation of the square minus the square of the expectation, standard definition of variance. The expectation of the square, well, with probability p, the square is 1. And with probability 1 minus p, it's 0. Meanwhile, here the expectation of the indicator variable is p, so its square is p squared. So the expectation of a single one of these indicator variables is p times 1 minus p, which means that the standard deviation, or sorry, the variance of this binomial is just equal to sp times 1 minus p. And now I can just remember that and never have to calculate it again, right? So now that I've got that, I can go back over to my analysis of median finding. And say that in our case, p is a quarter. So this is the variance, 3s over 16, right? So the standard deviation is root 3s over 4. And now I can plug that in to my Chebyshev bound, right? Having s over 2 small choices instead of what's the expected number of samples that'll be less than n over 4. Right? Chebyshev is measuring deviations from expectation. Yes. Right? That is a deviation by s over 4. Right? Which is how many standard deviations? Well, we said that the standard deviation is 3s over 4. Or sorry, let's just use the other Chebyshev bound, right? So the probability of this deviation, so this is my d in the Chebyshev bound, right? So I plug that in, and I get that it is at most the square of sigma squared, which is 3s over 16, divided by s over 4, right? The s's cancel, and I'm left with oh, sorry, thank you. S over 4 squared. That's very important, actually. So the 16s cancel, but I'm left with an extra s in the denominator, and so the probability is at most 3 over s, right? And this bound should make us happy. I would have been disturbed if I'd done my derivation, because what is expectable about this bound is that it decreases with s, right? The bigger your sample, the less likely you are to see a large deviation from the mean. Yes? Okay. The same analysis bounds the other side. Right? There's only a 3 over s chance that we'll have too many big samples. So we can say that the probability that we have a bad approximation outside the middle n over 2 items is at most 6 over s by the union bound. I just add the two bad probabilities. Okay. So we have proven an approximation. suppose I wanted to prove a better approximation. I wanted to show that we were within, median plus or minus 1%, plus or minus 1/100th instead of plus or minus a quarter. What would happen? What would change in this analysis? Is this sort of fundamentally dependent on my setting the boundaries at plus or minus n over 4? Yes? Exactly. If I set a different constant away from the middle, right? If I was talking about 1 over 100 instead of 1/4, it would change this p, right? But that's only a constant. That constant propagates through various things. But this analysis would still work. I would just get a different constant over the s. And so the probability is still inverse in s. And so by setting s to be a sufficiently large constant, I can drive the probability of an error down as small as I like. So essentially, what this really shows is that you can get any constant factor approximation for the right notion of constant factor with a constant number of samples. Is that clear? All right. Well, we're going to apply some of the same ideas to get an exact median finding algorithm. The idea is to clean up your approximation, or to use your approximation as a starting point to home in on the exact solution. Okay. So here we're going to use the idea that I mentioned last time, and this is an algorithm due to Floyd and Revest. So just as a sign of how young computer science is, right? This is not a very complicated algorithm, but Floyd was one of my teachers at graduate school, and Revest is still a professor here. So we're still in the lifetime of the people who invented the most basic algorithms in computer science, which is kind of weird when you think of mathematics as a contrast. All right, so the idea now is we're still going to pick S samples with replacement. But the problem now is that the median of the sample doesn't tell us enough to home in on an exact solution, because the median might be a little bit bigger than the sample median might be a little bit bigger than the true median. It might be a little bit smaller than the true median. We don't really know in which direction to go. Okay. But what I am going to do is use the sample to identify what I'm going to call fences that we know to be above and below the median, but close to it. We are then going to filter out the items that are outside the fences, and then we are going to find the median inside the fences. Okay, so going back to we have our x1 through xn. We have a sample subset. Right? My argument is that I'm going to find two elements in here. Here's my x sub n over 2. I'm going to find two elements in here that are guaranteed to be outside of, to be on the two different sides of the median, but not too far apart. I'm then going to scan through all of the items and throw away the ones that are outside of these two fences. I'm going to see as I go how many items are on the small side and how many are on the big outside. Right? Knowing how many are on the small outside, I know the index of the true median between the two fences, so I can just hunt for the element of that index inside of the two fences. So is the general idea clear so that I just need to work out the math? Great. So here it turns out that the right parameters are that I'm going to use S equal n to the 3/4 samples. Okay, so this is quite a bit larger than we were thinking about over here, right? Much bigger than a constant, but still negligible compared to n, right? I don't need to worry about the work of dealing with these samples. I can sort them to find the median, and it's lost in the noise of the overall computation, right? Okay. At the same time, intuitively, sort of the spacing between adjacent elements is only about n to the 1/4 elements. So we have a pretty fine resolution of sample of the entire set. Okay. And we're going to use the same idea that the rth sample is near index r times n over s. Let's just make sure that makes intuitive sense. So basically, if I double the number of samples, it's sort of halving the granularity of my indexes, right? But otherwise, it sort of scales linearly with the index in the sample. Okay. And then to find the median, we will look at fences A, which is going to be at index s over 2 minus square root of n, and B, which is at index s over 2 plus root n in the sample. So again, this is notionally where the median ought to be. And this is our fudge factor, that we're looking root n samples larger and root n samples smaller in order to get these fences. Okay. So to analyze this, we really have to prove two things. First, we have to prove that this is correct. And in order for it to be correct, we're going to need the true median to be between the fence posts, right? So we have to show that, in other words, x prime sub s over 2 minus root n is less than x sub n over 2, and x prime sub s over 2 plus root n is bigger than x sub n over 2. The second thing that we have to prove is that it is fast. What is going to make it fast? What's going to determine, well, what are the different steps of this algorithm, and what can we say about their cost? Well, one step is choosing the sample. This is not hard if you have an array and you want to sample with replacement, right? It's going to take time proportional to the number of samples. The next thing that you need to do is filter, right? Filtering just means taking each element and comparing it to the fences and deciding if it's on one side or the other, right? So sample is clearly fast. filtering, at least if you do it naively, takes exactly 2n time. Right? So the challenge is, or the question is, how long does it take to find the median between the fences? And that is determined by the number of items between the fences. So I have to show that that number is small, right? And if I show that this number is negligible, little o of n, then my runtime is 2n plus little o of n, and I've beaten the deterministic time bound. Okay. So we have to show that there are few items between the fences. That's the second step of the analysis. Okay. I'm going to prove one in class, and you have 2 on your homework. Yes?
Don't we also have to take into account the time the time expected?
Yes, but it's sorry. Let me say sample and pick fences. Okay. Because remember that our sample is small, right? And so all we can do, we just can sort it. And that takes time, which is negligible compared to n. Okay, good catch. All right. So let me prove part 1 for you. Part 2 is proven in a very similar way. And it's the same analysis as I did for the approximate median, just with some slightly different parameters, right? That's not right. Oh, yes, it is. Right. So I want to prove that A is before the median. Correct? In order to do that, I'm taking these independent samples, right? Each sample is below the median with probability 1/2. So I am working with binomial distribution with parameters s and 1/2, right? That implies that the variance in the number of items below the median is s times 1/2 or s over 4. Yes? So my sigma is equal to the square root of s over 4. Remember that s was n to the 3/4, so this is n to the 3/8 over 2. Yes? All right, so this is sort of the preparation, the parameters that I need. What is the bad event? What is going to cause my filter to be broken? Yes. Exactly. And that's because of the way I've chosen the parameters. But what is, in sort of planning, before we get to setting the parameters, what is the actual scenario that would cause my filter to be broken? Yeah? Yes, and those are the same analysis, symmetric. So here I'm only analyzing the median falling before A, right? And what would cause that to happen is if too many of my samples, all four fall before A. Yes. So the probability that less than S over 2 minus root n samples are below the median. That's a deviation by root n, which is about n to the 1/8 standard deviations. Say deviation by n to the 1/8 standard deviations. So its probability is less than n to the minus 1/4. Okay. Remember, this minus root n comes from how we chose our fence posts, right? Is this clear? Ask questions if it's not. All right. So we have an n to the minus 1/4 chance that A is a bad fence post. We have an n to the minus 1/4 chance that B is a bad fence post. So the probability that we have either bad fence post is less than 2n to the minus 1/4. Okay. So we're very unlikely to have bad fence posts. You will prove that we are also very unlikely to have a lot of items between the fence posts. Put those together, and we can conclude that the algorithm is extremely fast. It takes 2n comparisons plus little o of n. Now, as we discussed at the very end of last class, we can actually significantly improve on this. Do we actually need to spend 2n time filtering the items? Right? What's the natural way to do this filtering? Right? We compare it to A. Maybe it's too small, and then we just put it on the small side. Right? If it's bigger, well, then we have to compare it to B. And if it's too large, we put it on the B side. Right? So that sounds like 2 comparisons per item, but it isn't really. Right? Yes?
Like you can generally guess like whether it's like small or big, and then you can compare to the one that's like a half chance of like not needing a second comparison.
Great. So I can argue 50-50. Like it's either too small, most of the items are either too small or too big. So I'll just flip a coin. I'll compare it to the large fence or the small fence, and I have a 50-50 chance of throwing it out on the first comparison. Right? And so that would reduce my expected number of comparisons to only 3n over 2, right? Instead of 2n. Actually, you don't even need to randomize, right? If you think about it, if we picked good fence posts, it means that half the items are smaller, right? And so half of them are going to be discarded on the first comparison, deterministically, right? So it's going to be 3n over 2 even if I just compare to the small and then to the large, right? Unless my fence posts are bad, okay? So the result here is that we are going to do 3n over 2 plus order n to the 3/4 or so comparisons. Maybe there's a log n in there, but okay. Okay, and so this is better by 25% than the best possible deterministic algorithm. Okay. However, caveat, this is a Monte Carlo algorithm, right? What if we want a Las Vegas algorithm? What if we want to guarantee correctness? Well, the standard approach for getting a correct algorithm from a Monte Carlo algorithm is to test the answer, and if it is wrong, you try again, right? So we could do that here, right? We could check whether our fence posts are good. And if our fence posts are bad, we can just run the algorithm another time. Now, you might be a little concerned about this because as soon as we run the algorithm a second time, we're taking longer than the optimum, right? We're going to 3n comparisons instead of 2n comparisons. However, the chances that we do that are so small that it doesn't actually matter. In fact, we could just say that if we get it wrong on the first try, we'll just sort the whole array and take the median, right? Because the chances we get it wrong on the first try are only n to the minus 1/4. If that happens, we'll spend n log n time, but the contribution, that only contributes n to the 3/4 log n to the expectation, which is negligible. Okay, so this is a Monte Carlo algorithm, but we can turn it Las Vegas by just detecting when our fence posts are bad. All right, and that is, for the most part, the end of the story for median finding. I'm going to show you one more interesting thing about it, but we can pause here. Any questions? People are still working to push up the lower bound for deterministic median finding. And I think I can dig up the paper that currently has the best bound. It's like, 2.01 or something like that. But it's definitely bigger than 2. Yes?
What's the best deterministic algorithm that's been found?
That's a good question. I think that quick select might be it. What was that? Oh, sorry, the best deterministic algorithm. Yeah, I think that might be the the median of medians algorithm that you get taught in elementary algorithms. But I could be wrong. I don't pay attention to deterministic algorithms. So, right? Actually, I'll mention one other thing. You could, if you really care, you can tweak this a little bit more, okay? Because we have a subproblem of finding the median of the sample, right? So we could recurse on that if we really cared. Right? And once you make the median finding of the sample faster, it allows you to make the sample a little bit bigger so that you get a little more precision and the area between your fence posts is smaller, right? And so essentially you can make the next order term more like square root of n instead of n to the 3/4 if you really want to push things to their extreme. Okay, this is a perfect time for a break because I'm going to talk about an entirely different topic next. So grab your 2 minutes, and then we will resume. Oh no, everybody's sitting.
like this is a sorting algorithm that basically sorts the first 1/32 of the list, and then uses all of those elements as pivots for the rest of the list.
Yeah, sort of you're doing a binary search insert at that point.
Yeah, basically.
Yeah. Yeah, that's actually, there's an algorithm called box sort that you use in parallel algorithms, in parallel machines that has a bit of that nature. I'll probably talk about it at the end of the lecture, at the end of the semester.
All right.
It leads to very efficient parallelization.
Very interesting.
Yeah.
Because like the remark that I heard is that like because the algorithm like is defined recursively, even in the worst case, it's still O of n log n. Actually, is this true?
No, that's not true.
It's not true. Yeah.
If your first 32 pivots are all right at the front of the list, you're still going to be in trouble.
Or it's not 32 pivots. It's like n over 32.
Sorry, if your first n over 32 pivots are at the beginning of the list, you're still going to be in trouble.
That'd be like something like n log squared n. But
I don't think so.
The claim is that if you use like specific data structure, sort of like counting sort, then
it could be, but I think if you start with a truly random pivot set, there's a chance things are going to go horribly wrong.
Or like the worst case is that
If you use a deterministic median finding kind of approach, you can ensure that you don't get bad pivots. But if you just randomize, I don't think you're protected. All right, let's resume again. What I want to talk about next is a kind of weird idea that it took a theoretician to think of. We've been talking all this time, and we talk all the time in algorithms in general about running time, right? And that is the thing that we want to optimize. But we recognize that there can be other things that you might want to optimize. One that we do look at pretty often is space, right? Computations that take a lot of memory can be very bad. And so there's a lot of research into ways to solve problems without taking a lot of storage. And we're going to look at some of that later in the semester. We'll look briefly at streaming algorithms, which try and analyze massive amounts of data without storing a lot of it in memory. But we are now studying randomized algorithms, and so that actually produces a third resource that we can imagine trying to optimize, which is the randomness, right? The algorithms that we are developing consume random bits in order to drive themselves. And some theoreticians said, well, maybe that randomness is expensive, right? Maybe I need to build a nuclear power plant so that I can put up a Geiger counter and watch the decay of atoms in order to generate my truly random bits. And that's going to make those random bits very valuable, and I don't want to use too many of them, right? So there is a whole area of theoretical computer science that looks at that addresses this problem of treating randomness as a resource. Okay, and asks, okay, you've got this problem to solve. How can you do it using as few as possible random bits? Okay. And stated that way, it's clearly a very theoretical question. But there is a practical connection if we talk about pseudorandomness. So when you run a randomized algorithm on a typical computer, a lot of times it's not actually randomized. Instead, you're using something called a pseudorandom generator, right? And the idea of a pseudorandom generator is to create a stream of bits that looks random to an algorithm, that causes the algorithm to work as if it were getting random bits, but are not actually random because traditionally it's not actually been possible to generate random bits on a computer, right? Computers are deterministic machines, right? So instead they do weird mathy calculations and output numbers that you don't know where they came from, but they are still deterministic, okay? And so in an effort to explore and explain why this works, there was developed a theory of pseudo-random generators, Okay, a pseudorandom generator takes a small number of truly random bits and generates a large stream of bits that appear random to an algorithm that is using them. Okay, and what does appear random mean? It means that you've got this randomized algorithm, you've proven that it works, it has a certain expected running time, right? What you want is a pseudorandom generator that produces a stream of bits where your proof still works. Okay, so you can argue that if your algorithm is running not on a truly random stream, but on a pseudorandom stream generated by a certain generator, then your proof that its expected runtime is small is still valid. Yes?
When we talk about a pseudorandom generator, are they like saying like a generator for that algorithm?
It's a very good point. So, a very good question. So, the theory of pseudorandomness doesn't actually, these are theoreticians, they don't actually care about algorithms for solving problems. They immediately abstract the problem away to algorithms for detecting that your bits are not random. Okay? Because if you have an algorithm to solve a certain problem, what you can say is, if I run my algorithm on this pseudorandom bit stream and my algorithm doesn't solve the problem, I've just detected that the bit stream is not random, because I proved that my algorithm works when I have a random stream. So the only reason that it wouldn't be working, I mean, I could possibly code a bug into it. Rather, the only reason that it would not be working is that the stream is not actually random. So a randomized algorithm is actually a kind of detector of pseudorandom, of non-randomness. And there's a whole study of what kinds of detectors can detect what kinds of fake randomness. Right? And a pseudorandom generator is considered better if it can fool a broader class of these detectors of non-randomness. Okay? All right. So I'm going to give you a concrete example of a pseudorandom generator. Okay? The nice thing about these pseudorandom generators is that we do have designs for pseudorandom generators that can basically be plugged into algorithms and just work with no change in your analysis. If you've done a certain kind of analysis, it immediately means that you can use a certain kind of pseudorandom generator. And I'm going to give you one example of that right now. We have lots of algorithms. I'm sure if you think hard, you can come up with an example that, or whose analysis depends only on what's called the pairwise independence of certain generated random variables. Okay. What does pairwise independence mean? Well, I say that a collection of variables x1 through xn are pairwise independent if each pair, xi and xj, are independent. Seems like a pretty silly, wasteful, circular definition, right? Why don't I just call this independent? Yes? Exactly. So this is different from what's called mutual independence. Where all subsets are independent. Okay. So pairwise independence simply says things like the probability of xi and xj, if we take these to be indicator variables for the moment, is the probability of xi times the probability of xj. Right? Mutual independence also covers larger sets of variables, which pairwise independence does not. So pairwise independence is a weaker notion of independence. Okay. Now, is it strictly weaker? Can you have sets of variables that are pairwise independent but not mutually independent? And the answer is yes. Right? So, for example, if I make x1 and x2 independent coin flips, and I now define x3 to be the XOR of x1 and x2, I claim that I have three variables that are pairwise independent but not mutually independent. Okay. The point is that if I know one of them, it doesn't tell me anything about the value of another. But if I know two of them, it tells me everything about the value of the third. Right? If I know x1, then of course it tells me nothing about the value of x2 because x2 is independent. But it also tells me nothing about the value of x3 because x3 results from this independent x2. Right? And you can think about all the other combinations in the same way. So you can have pairwise independence without mutual independence. Okay. You can generalize this in several ways. There are different pseudorandom generators. So one generalization is if you're given, let's see here, which order do I want to do this? Yeah, if I'm given T independent bits, right, coin flips, I can define for a subset S, I can define x of S to be equal to the XOR over all of the items in S of those bits. Okay. And the point is that any two XS, x of S1 and x of S2 differ on some included variable, so are independent. Right? So this actually takes T independent bits and generates 2 to the T pairwise independent bits. So I get an exponential expansion in the number of bits I work with if I'm willing to settle for pairwise independence instead of mutual independence. Can anybody think of an algorithm where only pairwise independence matters? So that I don't have to change the analysis if I'm using these pairwise independent bits? Where did we do an analysis that sort of just relies on pairwise independence of variables? Yes? Elaborate. So Chebyshev bound does not refer to independence at all, right? Chebyshev bound just says the probability of deviation is a function of the variance. So can you?
To get the sum of the different variables variance.
Great. So we used in Chebyshev's bound that the variance of a sum is equal to the sum of the variances. That's what made Chebyshev's bound really easy to apply, right? But that claim that the variance, and I said that that's true when the variables are independent. But if you look at how that claim is proven, right, we take the sum of this, we take the expectation of the square of the sum, right? So write that out here. Example of where pairwise independence is all that matters, right? Variance of a sum is comes from, I'm not going to write out the whole formula, but what matters is the expectation of the sum of the squares of the x's, right? Which looks something like a sum of expectation of products of pairs, but only of pairs, right? So this becomes a sum of products of expectations if the xi are pairwise independent, right? So having pairwise independent x's is enough to let you conclude that the variance of a sum is the sum of the variances, and that's all that we used in our analysis of quicksort. Okay. Now, so far I've only told you about how to generate pairwise independent bits, and we need more than pairwise independent bits in order to run quicksort, right? So I have to fill in some details, but you see how we only need pairwise independence if we're using Chebyshev's bound. And this is why I didn't use the Chernoff bound. That's what somebody asked me that at the beginning of class, right? The Chernoff bound requires more than pairwise independence. So let me show you another pairwise independent pseudo-random generator, which is good for generating more than just bits. Let's talk about generating pairwise independent random variables over ZP. So I'm going to assume that most of you have seen modulo arithmetic, clock arithmetic, right? So ZP is integers modulo P. And of course, I use P because P is a prime. If P is a prime, then ZP is a field. Okay. So we all know how to do addition in clock arithmetic, and that makes it easy to do multiplication in clock arithmetic. But if you have addition and multiplication, you can start asking for subtraction and division, which requires a notion of inverses, additive inverses, and multiplicative inverses, right? And the fact is that if you're working modulo a prime, well, the definition of an additive inverse is obvious, right? You just go the other way on the clock. But what is surprising and wonderful from number theory is that there's also always a multiplicative inverse. Okay? And this actually comes from Euclid's algorithm. You can go off and prove it if you don't know it. So we can go ahead and talk about division and subtraction in prime modulus fields. And this is the only number theory I'm going to do the entire semester. So if you don't have it, it won't hurt you. What we're going to do is, to generate random numbers, given truly random A and B in ZP, So if you pick truly at random twice from this field, I'm going to define xi to be equal to ai plus b mod p. And I claim that these are now pairwise independent x's. This, by the way, this may be setting off some alarm bells for people who studied hashing with me last year. And I will cover this when I cover hashing next week. This is related to universal hashing. I claim that xi and xj are independent. Since I'm only talking about two of them, I don't need to specify pairwise or mutual. They mean the same thing. Okay. What is the proof of this? What I need to study is the probability that xi equals some s and xj equals some t. And I need to show that this is equal to the probability that xi is equal to s times the probability, right? That's the definition of independence. Yes? So how do I prove that? Well, the probability that xi is equal to s, this is the probability that ai plus b equals s and aj plus b is equal to t. Yes? So I'm going to write this out as a matrix problem. I want to end up with s and t. Let's see. I forgot to put this in my notes, so I have to reinvent it. Yeah, I think it's a. No. Yeah, I1, J1 times AB. Right? This is the matrix statement of what I am evaluating, right? So I am randomly choosing A and B, and I'm asking for the probability that I end up with a particular S and T. Okay? Now, how would I solve this matrix problem? Well, I could invert. Right? Can I invert? Can I write the inverse of this matrix? Why? Yeah? Exactly. It's non-singular matrix. And this is where I'm using the fact that ZP is a field, right? To be able to compute this inverse, okay? So I compute this, and now this gives me a specific value of A and B that have to be chosen in order for me to end up with S and T. And you know, since A and B are being chosen uniformly at random, right, the probability of this happening is basically 1 over p squared, right? There's exactly one pair of values, A and B, that work. So the probability of getting that A and B is 1 over p squared. And meanwhile, the probability of getting a particular S or a particular T, well, you just need to argue that this is choosing uniformly among the possible values, right? It doesn't matter. What's happening here doesn't matter, because in the end, you add a random value that just spins the clock, right? So each of these probabilities is 1 over p. This probability is 1 over p squared, and we're done. So this is a pairwise independent pseudorandom number generator. Okay. And you can now use, this one is letting you choose numbers in the range from 1 to p instead of just bits, right? And so if I go back to my quicksort algorithm, that's good enough, right? What I can do, for my sampling algorithm, I need to choose numbers from 1 to n. And as a theoretician, I could just assume without loss of generality that n is a prime. Or I could just use a really big P and then take that value mod n, right, and argue that it only introduces a little bit of non-uniformity in the distribution over n. Right? I could even be more careful and argue that I'm just very unlikely to pick the numbers that are at the very end, that are very close to P, and so probably I'm just picking from some multiple of n all the time. Okay? So I'm not going to spend time on those sketchy details. I will just argue that using this pseudo-random number generator, I can run my quicksort algorithm with only 2 random choices from numbers of size about n, instead of running n to the 3/4 choices of numbers of size about n. So that's an example of conserving randomness. Okay. Another more general example here. Suppose that we have any RP algorithm, right, which succeeds with probability 1/2. Yes, a question?
Oh, no, that's why I said large. I was going to ask if we wouldn't get that many.
That's right. That's right. So if we have any RP algorithm, okay, this has a success probability of 1/2. Right? So if we run it t times, and so let's say it uses n random bits. Okay. So if we run it t times, we can improve the success probability or the failure probability down to 2 to the minus t, right? We're using t-independent t-independent runs of this RP algorithm, but this is going to cost us tn bits, right? Because we need n bits for each run. Okay. Suppose that we only have 2n bits. So again, this is an example of how theoreticians think about randomness as a resource in the context of complexity theory. Right? So one thing we could do is run 2 independent trials of the algorithm and therefore reduce our failure probability to 1/4. But can we do better? Well, with pseudorandom generators, the answer is yes. Right? What we're going to do is we're going to set P around we're going to set P around 2 to the n. So each run needs a number from ZP. Okay. And notice that when you choose a random number in this range, you get n independent random bits, right? Modulo the fact that P is not exactly a power of 2, but again, I'm not worrying about the fudge factor at the edge. Okay. So choosing one number from ZP is enough to run the algorithm once. But we've just said that we can use a pseudorandom generator to do this, right? So imagine a pairwise independent based analysis. Right? Up here, I assumed t independent trials and drove the error probability down to 2 to the minus t, but that needed a lot of random bits. Let's just try a pairwise independent analysis instead. Mu, the expected number of successes. Or do I want to look at successes or failures? That doesn't really matter. Mu is equal to t over 2. if I run the algorithm t times, right? The standard deviation, well, if each run has a 50% chance of success, then the number of successes is a binomial distribution. We've already looked at the variance of a binomial distribution, right? And here we have our p equal to 1/2. So the variances add, which means the standard deviation is the square root of that added variance, and will just be square root of t over 2. This is the same sort of argument as we made for the median finding algorithm, right? We have an error if the number of actual successes of the algorithm. Remember that RP is one-sided error, right? So in order for you to fail, you have to fail every single time, right? The number of successes has to be 0. If the algorithm does the right thing even once, then you'll get the right answer. Okay. So we have an error if the number of successes is 0. In other words, y minus the expectation of y is t over 2, right? Because the expectation is t over 2. And that means, and this has the probability of this event, right? This is square root of t deviations, square root of t standard deviations away from the mean, right? The mean is t over 2, and our deviation is t over 2, so that's square root of t standard deviations away. So the probability of this is the square of the number of standard deviations, or 1 over t squared. Okay. Yes? We need 2 prime numbers, two